Assalamu alaikum dear students, I hope you all are fine in the best conditions of your health. So in today's lecture we shall study about the structure activity relationship, and this is continuation of the previous lecture on structure activity relationship. In this lecture we shall study about a bit of review about the structure activity relationship and how different physical and chemical properties have their effect on the biological action of the drug. So structure activity relationship, just as a review, structure activity relationship deals with the effect of changes in structure on the biological activity, right? So if two things have similar structure, we say that they should have similar biological activity, and a slight change in any structure will result in the change in biological activity, right? So here we shall see that how the changes in physical properties will result in change in the biological activity. Similarly, we'll see that how we can change the chemical properties of a molecule and see how that has effect on the biological action of the drug. So firstly, we'll see the effect of physical properties on the biological action of drugs. See, a drug can only effect its action when it is given in proper dose through proper suitable route of administration, right? So far we have discussed that we have a drug. Drug is anything that has some biological response, that has some biological effect on our body or on the biological system, right? And then we saw that how we can discover a lead. So firstly we have a lot of compounds, and then among them we get a compound which has a certain desired biological activity, so we call that a hit. We modify the hit to get an optimum structure, that's called a lead, and then the lead can be modified further, right? So suppose that we have got a very good drug that has the potential to show biological activity with least number of side effects. Now we are introducing that drug inside the body, right? So this drug, when inside the body, that can show its biological effect only when it is given in a proper dosage form. So if you give a drug in very less amount, maybe it's not able to show its action, and if you are giving a drug in a very high amount, that maybe the poisoning due to excess of drug may occur. The second thing is that the drug should be given through a certain suitable route of administration. So certain drugs can only be given through mouth. We say that these drugs are administered orally, and some are given through the blood in the form of injection or in the form of drips. So the drugs are applied in the form of cream or ointments, right? So it's important for you to know that it's not only that you have discovered a best structure and then your work is finished. So drugs can only show their physiological or biological effect when they are given in proper dosage form and through suitable route of administration. So once again a drug gets administered inside a body, so it should get dissolved if it's a solid, and it should get absorbed if it's a liquid or semi-solid or a gel form, right? So if a drug does not get dissolved or absorbed, it cannot show its action, right? So once it gets dissolved or absorbed, it gets into the circulation, and once into the circulation, that has to reach certain receptor for binding, right? So drug can only show its action once it's bonded with the receptor. So there are many physiological factors that have to be considered for optimizing the biological action of drug, right? So we have to ensure that this drug which we have made should bind with the receptor. So there are certain factors which have to be optimized so that we ensure that our drug binds with the receptor in the proper way. So these factors include ionization, solubility, pKa, hydrogen bonding, the protein binding, isomerization, chelation, and bioisosterism. So we'll see about how these factors affect the biological activity. So just for an overview, we have drug. We have considered the drug in proper dosage form. So we have calculated the dose which we will be given to it. So this drug must get solubilized inside the body, right? The factors which affect the solubility of the drug include the ionization, the pKa of the drug, the ability of the drug to form hydrogen bonding, and the type of isomerism which is existing in the drug. So once this drug gets solubilized, it has to be absorbed inside the biological system, right? It has to be absorbed by the cell membrane. So how the drug gets through the cell membrane, or how the gas is absorbed into the cell, that's determined by the partition coefficient. And the partition coefficient is dependent on the hydrophilicity of the drug, the lipophilicity of the drug, and again the ionization of the drug. So after the drug is absorbed, it must bind with the receptor, right? So in order to bind with the receptor, show the biological action, so it's important that the drug should have proper binding with the protein or with the receptor, right? So today's lecture will be discussing about these factors, how they ensure the drug is properly solubilized, is properly absorbed, and it properly binds with the receptor to show the biological action. The first factor is ionization. That's a very prime function which affects the drug absorption and its action. So it's a general rule that unionized drugs are easily absorbed through the gastrointestinal tract through process of passive diffusion. So what's passive diffusion? The diffusion is a process in which molecules move from higher concentration to lower concentration, right? And if the diffusion process is without any involvement of energy, you're not giving any energy for diffusion to occur, this is known as passive diffusion. But if the diffusion is occurring, if the transfer is occurring with input of energy, that will be the active transport, right? So unionized drugs are easily absorbed through the gastrointestinal tract, and this transfer, this absorption does not require any energy. The ionization of the drug, whether the drug will be ionized or not, that's dependent on the pH of the absorption site. The theory which deals with the effect of pH on the absorption of the drug is known as pH partition theory. So the silent features of this partition theory are that most of the drugs are either weakly acidic or weakly basic. Secondly, the unionized forms of drug, whether they are acidic drug or basic drugs, they are preferentially absorbed, right? So lastly, in the previous slide we also saw that the unionized drugs are easily absorbed. So unionized drugs, whether they are weak acid or weak bases, they are preferentially absorbed by the system. If the drug is acidic or if it's neutral, then it will be absorbed in the stomach. Why? Because stomach has an acidic medium. So acidic medium will prevent ionization of this weak acid. So our acidic drug will remain unionized, so it will be absorbed. While if you are taking a basic drug, so basic drug will not be absorbed in the stomach because basic drug will become ionized under acidic medium, right? So it's important for the drug to be unionized for it to be absorbed. Secondly, the weakly basic drugs are absorbed in the intestine. Why? Because intestine have the bile juices, and bile juices are alkaline, they are basic. So because of the basic medium, the basic drugs are not ionized because this basic medium prevents ionization of the basic drug, and they remain unionized. So in unionized form, the weak bases are absorbed, weakly basic drugs are absorbed in the intestine, while acidic drugs become ionized in this medium, so they are not absorbed in the intestine, right? So this is pH partition theory. Now, ionization of the drug, or the percentage of the drug that exists in unionized form, right, that depends on the pH of the medium, or since we are considering about the biological system, so this ionization or the percentage of the drug that remains unionized is dependent on the pH of site of absorption, and it also depends on the dissociation constant of the drug, right? So consider that we have an unionized acid, so in aqueous medium, and that is an equilibrium process. So this unionized acid will transfer its proton to form a conjugated acid, which is a hydronium ion and a conjugate base, right? So we can write this equilibrium constant, this dissociation constant, as Ka into concentration of hydronium ion, concentration of conjugate base, divided by concentration of the HA. So since water is in excess, so don't consider water in this equilibrium expression. So this is the equation for the acid dissociation constant. This is an unionized acid, right? And we know that negative log of this Ka is equal to pKa here, and we also know that relationship of Ka and pKb is pKa is equal to 14 minus pKb, right? So here you can calculate the percentage ionization of an unionized acid, and also you can calculate the percentage ionization for an ionized acid, right? So you can tell that which percentage of the unionized acid has been ionized and what's the percentage of ionized acid, right? You can calculate both by this simple formula. So the formula is, if you have to calculate the percentage ionization for an unionized acid, you have to divide 100 by 1 plus 10 to the power pKa minus pH. And if you are calculating the percentage ionization for ionized acid, then same formula except that 10 to the power pH minus pKa, right? So here we had pKa minus pH, but now we will have pH minus pKa. So just for an example, let's consider the chemical structure of the ciprofloxacin. So this structure of ciprofloxacin, here we have acidic group, which is carboxylic group, that's weakly acidic. And here we have these nitrogens, these are the amines, so amines are weakly basic. Here we have ketonic group and fluoro group. So ketones and halogens, they are considered as neutral groups, so they don't interact with the acidic or basic pH. So what happens that when we have highly acidic pH, then this basic groups will get protonated, right? So they will not be absorbed, right? And the acidic group remains unionized because the acidity in the stomach prevents ionization of this acid. While under neutral conditions, what happens that both of these groups are ionized. We say that these are existing in the form of deuterion, right? The carboxylic acid group is also ionized and the amino group is also ionized. But if we consider the pH at about a higher value, that is under alkaline conditions, then under alkaline conditions this amine will not be ionized, however this carboxylic acid will be ionized, right? So this is an example in which you say that suppose if we didn't have that fragment, then under acidic conditions, so the acid is not ionized, so that will be absorbed. Under basic conditions, if we didn't have that carboxylic acid group, then the basic drug would be absorbed and the acidic group will remain ionized and will become ionized, right? So it's important for the drug to be unionized for better absorption. The second parameter is the partition coefficient. So some drugs are, although they are unionized, they are not properly absorbed after oral administration. So what we mean by oral administration, it means that if you take a drug by mouth, that is oral administration, right? So some drugs, although they are unionized, but still they are not properly absorbed after oral administration, right? So there is an important factor here we will consider, and that important factor is the partition coefficient, right? So what's the partition coefficient? Consider that a drug is added to a system and that system is consisting of two liquids and both are immiscible, right? Then the drug tends to distribute itself between the two liquids until an equilibrium is achieved, right? So depending upon the affinity of the drug for either the aqueous phase or the organic phase, the drug will distribute itself between the two liquids until there is an equilibrium, and this process is known as the drug distribution. Partition coefficient affect drug's absorption, and since after absorption it will become it will have to be bonded with the receptor, so ultimately the partition coefficient not only affects the drug's absorption but also it affects the biological activity. It also affects the transport of the drug and the structure-activity relationship of the drug, right? And further, it's also responsible for the lipid solubility of any drug. So let's consider this factor in a bit detail. So if you have to define the partition coefficient, it can be defined as the ratio of drug concentration in aqueous phase to its concentration in it's the ratio of the drug's concentration in organic phase to the concentration in aqueous phase. The extent of absorption of a drug through passive diffusion greatly depends on lipophilicity, right? So if you want the drug to pass through your cell membrane, which is non-polar, so in that case the drug must be greatly soluble, highly soluble in the organic phase, means partition coefficient should be higher, right? So the efficiency of the drug in partitioning between the two phases, right? So if you can summarize, you know that drugs which have higher partition coefficient are the drugs that are highly soluble in the organic phase, and since they are highly soluble in the organic phase, they are more lipophilic, and therefore they absorb readily through the lipid bilayer of the cell membrane and show better biological response. And the drugs that are more hydrophilic, they have lower partition coefficient, right? Because their concentration in aqueous phase is higher, therefore the partition coefficient value will decrease. So drugs that are more hydrophilic means they have greater solubility in water, they have lower partition coefficient, right? So they are preferentially found in high concentration in the blood, so they find difficulty in moving through the cell membrane. It's important for us to know, number one, the first factor is that preferentially the drug should be unionized, and second, we are saying here that partition coefficient must have some reasonable value, right? And it should be such that the lipid profile or the lipophilicity should be significant so that your drug must be able to pass through the biological membrane. The third factor is the solubility. So the ability of drug to dissolve in a solvent is called solubility, and it's measured in terms of the drug dissolved in solvent at equilibrium, forming a saturated solution under fixed set of temperature, pressure, and pH. Right? So the amount of drug that's dissolved in a solvent to form a saturated solution, that's called solubility. So it's important for the drug to be absorbed, must be present in solution form at the site of absorption, because if a drug is not present in solution form, it cannot be absorbed, right? For example, for orally administered drugs, means the drugs that you are taking through mouth, the solubility is very important, rate limiting parameter, right? Because once this drug is absorbed, that will enter directly into the bloodstream for maximum biological action, right? So if the drug is taken orally and the drug does not become soluble, if it's not becoming soluble, it will not be absorbed. Right? So solubility is a very important factor. So firstly we saw about ionization. So ionization was dealing with the absorption. Then we have partition coefficient. Partition coefficient was dealing with the absorption. And here we have solubility. Right? So if a thing does not become soluble, that will not be absorbed ultimately. So we have to get things solubilized. Depending on the solubility of the drugs are classified as follows, right? So drugs may be called as very soluble, freely soluble, soluble, sparingly soluble, slightly soluble, very less soluble, depending on the amount of solvent used, right? So if you use 1 part of solvent to dissolve 1 part of solute, we say the drug is very soluble. However, if you use 1 to 10 parts of solvent to dissolve 1 part of solute, we say drug is freely soluble. If we have to use 10 to 30 parts of the solvent, then the drug is called soluble. If we have to use 30 to 100 parts of solvent to dissolve 1 part of solute, we say the drug is sparingly soluble. And if you have to use 100 to 1000 parts of solvent to dissolve 1 part of solute, we say it's slightly soluble. And if we have to use 1000 to 10,000 parts of solvent to dissolve 1 part of solute, we say the drug is very less soluble. The solubility of the drug is affected by its partition coefficient, right? So if a drug has higher partition coefficient, that will be more lipophilic. If it has a lower partition coefficient, that will be more water soluble. Then we have dissociation constant, right? So if a drug is more in unionized form, then in that case the dissociation constant value will be lower and the drug will be absorbed more. Then we have hydrogen bonding, then we have ionic interactions, also the molecular size and shape of drug matters, and the lattice energy and the melting point of the drug also matters. So all of these factors, they somehow are related with the intermolecular forces, right? So according to the biopharmaceutical classification system, which is normally abbreviated as BCS, right? So we have 4 classes of drugs. Class 1 are known as the highly soluble, highly permeable drugs. They are best soluble for the drugs that are to be used for immediate release, right? So if you need immediate response from a drug, you should use a class 1 drug. That is the drugs that are highly soluble and highly permeable. They are highly soluble and are absorbed readily because they are permeable through the cell membrane. So examples are propranolol, labetalol, then we have enalapril, then we have diltiazem. So all of these are class 1 drugs. Next we have class 2 drugs. They are low soluble but they are highly permeable. So you can easily see that the solubility is a rate determining step. So once that drug becomes soluble, that will immediately enter the cell membrane. So solubility is the determining factor. So if the solubility does not allow the drug to be absorbed, the drug will not show its action. But if the solubility becomes reasonable, the drug will show its action immediately. The examples of such drugs are the flurbiprofen, diclofenac, we have piroxicam and phenytoin. So all of these belong to class 2 drugs. The third category is the highly soluble or the low permeable drugs, right? Although they are highly soluble, but they are not easily absorbed. So here the permeability or this absorption is a rate determining step. So once the drug enters into the cell membrane, that will be absorbed, right? So here the problem is solubility. All the is the absorption or is absorption to the cell membrane, right? So here is the relative step. Although the drug is available in soluble form, but it's not permeable, right? So drug cannot enter into the cell membrane. So once it enters into cell membrane, that will show its action. So examples are famotidine, erinolol, ranitidine, cimetidine. Next is the class 4 drugs. These are low soluble and low permeable, so they are not absorbed properly and they are not suitable. So we're not giving any example of such drugs because such category are not used as drugs normally. So when we are considering that once you have taken the drug and the drug is inside your body and you have to calculate what's the maximum absorbable dose, right? So you have suppose given a 500 mg of a drug and you want to know that how much of it is absorbed actually. So you can calculate that, and this dose is known as maximum absorbable dose. So maximum absorbable dose, also known as MAD, is the maximum amount of drug that can be absorbed at a certain dose. It can be calculated as that's equal to solubility multiplied by the intestinal absorption rate constant multiplied by the water volume in the small intestine and multiplied by the transit time in the small intestine. So transit time is actually the time that a drug takes to pass through the small intestine, right? So if you have these factors, you can calculate the actual maximum absorbable dose that will be actually absorbed, that will maximum absorbed inside a system. Right, so suppose that we have a drug and it has some solubility issues. We want to make it more water soluble, right? So what we can do is that we can modify the structure of the drug molecule. And how we can modify to make it more polar? We can add ionizable groups, such as we can add basic amine or SD carboxylic acid. So by attaching these ionizable groups, we can improve solubility. Second way is that we can add some groups which are capable of hydrogen bonding. So because of hydrogen bonding, the water solubility will increase. Thirdly, we can add some polar groups. So those polar groups will also increase the water solubility. So in case you're thinking about the reverse, you want to make a thing more lipophilic, so you will go for the reverse. So instead of addition of ionizable group, you will tend to reduce the number of ionizable groups, or you can remove the number of hydrogen bonds, or you can remove some polar groups, right? So by adding or removing these groups, you can modify the solubility of your drug molecule. Next important factor is the hydrogen bonding. So you know that's very important type of van der Waals forces, and it is the most important factor that's responsible for the aqueous solubility of the organic compounds. So there are two types of hydrogen bonding. So you know that there are intermolecular and intramolecular hydrogen bonding, right? So these type of hydrogen bonding, they are not only responsible for the solubility of drug, but they are also responsible for chelation and binding with the receptor. So previously we saw that lipophilicity is very important for the drug to enter into the cell membrane. Lipophilicity is important, but aqueous solubility is also important because aqueous solubility is essential for the transport of drug molecules to the site of action. because the drug has to enter the bloodstream and then reach the site of action, and the medium of this blood is water, right? So it's important for the drug to have some aqueous solubility so that it can be transported through blood to the receptor site, right? So by increasing or by managing the hydrogen bonds, we can modify the water solubility or the aqueous solubility of the drug. So in general, greater the number of hydrogen bonds, more will be the aqueous solubility, right? So we can increase or we can decrease aqueous solubility by managing the number of hydrogen bonds in a molecule. So common atoms that are capable of hydrogen bonding are oxygen, nitrogen, fluorine, chlorine, and sulfur. Let's take an example of effect of hydrogen bonding on the biological activity. So here we have this structure. This is 1-phenyl 3-methyl aspirazolone. So this molecule had the problem that it has no analgesic activity. It's water soluble, right? Some problem because of that it's not water soluble, and it's slightly soluble in ether. So what happens, why it's not showing solubility in water and why it's not showing solubility in ether, is because this molecule, because of hydrogen bonding, that forms linear polymer, right? So molecule like that, so if you just imagine that we have another molecule, so this hydrogen of nitrogen and this oxygen of the carbon, they are linked together by means of hydrogen bonding. So they form a linear polymer, and because of that linear polymer, that's because of the effective molecular weight is increasing, right? So because of the larger size of that polymer, this polymer becomes insoluble in water, so its aqueous solubility is decreasing. Further, it's also not soluble in the organic phase as well, right? So that's not becoming soluble, and because of lack of solubility, it's not showing the analgesic property. So what we do is that in order to make this molecule more better in analgesic activity, we stop this hydrogen bonding. And how we stop this hydrogen bonding? We replace this hydrogen with a methyl group here, right? So with this hydrogen gone, so it cannot show the hydrogen bonding, and it will not form that molecule, that polymer. So by removing this hydrogen and replacing it with methyl group, now you can see that it is good analgesic agent, and solubility in water has improved, and solubility in ether has also improved, right? So this was not having any biological action, but by just replacing this hydrogen with methyl group, we have improved the solubility. Another example here, we show that we have orthohydroxybenzoic acid, known as salicylic acid, right? So salicylic acid has a pKa value of 3. It is less water soluble. You can see the reason why, because it is having intramolecular hydrogen bonding, right? So always remember that intramolecular hydrogen bonding causes decrease in solubility, while intermolecular hydrogen bonding causes increase in solubility, right? So this molecule has good antibacterial action, and it has less water solubility, while this orthohydroxybenzoic acid, right, that has pK value of 4.5, and it is more water soluble. You can see the reason why it's becoming water soluble, because of the intermolecular hydrogen bonding, and it has low antibacterial action. So now why the reason is that because that is more water soluble, so it's not able to go through the cell membrane of the bacteria, right? So, and since it's not able to enter through the cell membrane of the bacterium, so it's showing the less antibacterial action. Now this drug, that's less water soluble, but that's more lipophilic, right? So because of its lipophilicity, it is better in entering the bacterial cell wall, right? So it has greater action and it has lower action. So hydrogen bonding between the water molecules and the drug may be like hydrogen bond and the dipole interactions. So alcohols, aldehydes, and esters, they form the hydrogen bonds via the hydrogen bond and dipole attraction. So here we have a dipole of this alcohol or aldehyde or an ester, and here we have the hydrogen bonding, right? So alcohols can form 3 hydrogen bonds with this water molecule. Then we have aldehydes. Aldehydes can form 2 hydrogen bonds with the water molecule, and this ester can form 3 hydrogen bonds with the water molecule. Alternately, hydrogen bond can also exist between the water and the ion dipoles. So if you have an amine, and this amine is existing in acidic form, in ionized form, right? So this is example of the ion dipole, and this is also example of ion dipole and the hydrogen bonding interaction. So both type of interactions can exist for hydrogen bonding. So hydrogen bonds can be between two neutral molecules, that water and a neutral molecule, and it also can be between water and some ionic species. So after we have studied about the physical properties, now we will consider about the biological actions or the biological activities. So among the chemical properties which affect the biological action, so let's consider about the protein binding. Many drugs, once enter into circulation system, they get bound to plasma proteins. So majorly there are four types of plasma proteins which are present in the blood. They are the albumin, glycoproteins, lipoproteins, and globulins, right? So what happens that once the drug enters into the bloodstream, that gets binded to these proteins, and they form a drug protein complex, and we say that drug is now in bound state, right? So once the drug forms the drug protein complex, its size becomes too large to pass through the cell membrane, right? So in the bound form, the drug cannot enter into the cell. So how much the drug is bounded to the protein, that is the degree of protein binding, it affects greatly about the drug pharmacokinetic properties. So always remember that it's the free drug that is responsible for biological action. So if a drug is not present in free form, it will not be able to show its biological action. So what happens as a result of this drug protein complex, that the distribution of the drug into the various parts of the body is reduced. Because the drug is in the bound state, it cannot enter into the cell membrane, therefore the distribution is restricted. Second, the biological activity of the drug is reduced because the drug is not available in free form. So since there is no free drug, it will not be available for binding with a receptor. As a result, the biological activity of the drug is decreased. Third consequence is that the duration of action of the drug is prolonged or delayed, because the drug takes very long time to dissociate from the complex and become available for binding with the receptor. Fourth, due to the large size of the complex, this complex cannot be eliminated from the body. So the problem of excretion from the body becomes a very significant one. And fifth is the most important thing, is that most of the time this drug protein complex has toxic effects. Therefore, since it cannot be eliminated from the body, so it gets accumulated in the body, and because of accumulation of this complex, so we experience facing some harmful effects of this drug protein complex. So this drug binding is of two types: reversible binding and the irreversible binding. So most of the acidic drugs, they bind reversibly to the proteins, most commonly with the albumin, and the basic or neutral drugs most commonly bind with this alpha acid glycoproteins. So this binding is reversible. It's of short duration, and once the concentration of free drug in the body decreases, the equilibrium will move towards the formation of this free drug. So this is an equilibrium process, right? So what happens that when the concentration of this free drug in the body decreases, the equilibrium will move in the reverse direction and result in formation of more free drug, right? So this is reversible binding. However, when there is a covalent bond between drug and protein, so when the drug forms covalent bond with the protein, then this is irreversible binding, right? So they become one structure. So that's now one molecule. That's not some conjugate. That has become one molecule, and this bond cannot be broken. And we say that the drug has been wasted. Alright, so you have to take in more drug so that becomes available for binding with the receptor, because in this form, in the case of irreversible binding, the drug is not available for binding at all. So after the protein binding, we have another factor, which is stereoisomers. So we have optical isomers and the geometrical isomers. So stereoisomers are defined as the isomers which only differ in their geometrical arrangement. So these stereoisomers may be configurational isomers, or they may be conformational isomers. So you know the configurational isomers are geometrical and optical isomers, right? So the difference between these isomers is that The configurational isomers cannot be interconverted by simple free rotation along carbon-carbon bond, while conformational isomers are constantly being interconverted into different conformers. Right? So the stereoisomers, due to their different 3D arrangement of atoms, they bind differently with the receptor. Right? So because of different binding with the receptors, different stereoisomers have different biological responses. So if you replace one isomer with the other, so you will change the biological activity also. So let's consider some examples. So here we have these enantiomers of the naproxen sodium, S isomer and the R isomer. Both of these isomers have different biological activities. Similarly, we have two another isomers. So one of these is analgesic. Just see the arrangement of atoms. So there is only one just change in arrangement of atoms, right? So one of these is analgesic while other is antitussive. Similarly, we have two isomers. So one is Z isomer, other is E isomer. So one isomer is inactive while the other isomer is an active isomer. It has some biological activity. Right. So there are some differences in the pharmacokinetic and pharmacodynamic properties of the stereoisomers. Just for example, we are taking some example in order to elaborate that difference in the stereoisomer result in different properties. So firstly, we'll consider the pharmacodynamic or pharmacokinetic properties, that's absorption. So the L isomer of the methotrexate is better absorbed than the D isomer. Similarly, among distribution, so the S-warfarin, that's a drug, is more bonded to albumin protein, while the R isomer is not bonded with albumin protein. Metabolism, so S-warfarin is metabolized by ring oxidation, while its R isomer is metabolized by the oxidation of the side chain. Alright, so both have similar structure, just a change in arrangement, but the S isomer that's metabolized by ring oxidation, while the R isomer is metabolized by oxidation of the side chain. Then we have difference in biological activity. So we have L-sotalol, that's an alpha blocker, whereas the D isomer is antiarrhythmic. Right, so we have changes in the biological activity. So one isomer is alpha blocker while other is antiarrhythmic. Then we have D-ethambutol, that's antitubercular, but its S isomer causes blindness. This is a typical example in which one isomer has some biological activity while other has harmful effect. Then we have dextromethorphan cough suppressant, while its other isomer, there's a levomethotrexate, that's an analgesic. This has an opioid analgesic effect. So why this difference in biological activity of the isomer? So difference in biological activity of the isomer is due to three reasons. Because you should know that biological system is itself chiral, and the stereoisomers are also chiral, right? So these enantiomers, when inside the chiral environment, they behave differently, and because of their different behavior, they are differently distributed in the body. They react differently with the receptor, so therefore there's a difference in drug receptor binding, and there's difference in absorption of the isomers to the receptor surface. Right, so the basic reason is why, because the stereoisomers are also chiral because of the asymmetry, and the biological system is also chiral. So because of this chirality, because of this difference in arrangement of the atoms, so there is difference in distribution in the body, there is difference in the drug receptor binding, and there is difference in the absorption of the isomer to the complementary surface of the receptor. Just for example, we are taking two isomers. So one is trans isomer and another is cis isomer. So both of these are tripolidine, and both of these are H1 antagonist, right? But cis isomer is 1,000 times less potent, and the trans isomer is 1,000 times more potent than the cis isomer. So here we have a hypothesis that's very important when you are considering the stereoisomers. This hypothesis is known as Easson-Stedman hypothesis. So according to this hypothesis, the difference in biological activity between enantiomer results from selective reactivity of an enantiomer with its receptor. So if you have two isomers, if you have two enantiomers, one of these will be more reactive, and the isomer which is able to form a 3-point fit with the receptor will have more activity, will be more potent. So just for example, let's consider these two isomers. So here you can say that this A is binding with this A prime, so that's complementary to A, so this is binding with A. B is binding with this B prime, C is binding with C prime, so this enantiomer is able to form a 3-point fit. So because that's able to form a 3-point fit, that will be biologically active. While this isomer here, you can say that this D is trying to bind with A, which is not possible, so that's not a binding. So this B is binding with B prime and C is binding with C prime, so that's forming a 2-point fit. So according to Easson and Stedman hypothesis, the two isomers will be biologically inactive, while this one isomer will be biologically active because that's forming a 3-point fit. Now we have conformational isomers. So conformational isomer is a dynamic process because these isomers are constantly being interconverted into one another. So that's the isomerization process that involves the free rotation along carbon-carbon single bond. So there may be free rotation about one carbon-carbon single bond or more than one carbon-carbon single bond. So in order to elaborate this process, let's take an example of the neurotransmitter acetylcholine. So this is the structure of acetylcholine, and we are considering that free rotation along this carbon-carbon single bond. So let's consider that this carbon is an alpha carbon and this carbon is the beta carbon, right? So this rotation along C alpha and C beta produces different arrangements, right? So when the ester and the trimethylamine group are 180 degree apart, we say that this is the anti-conformation or the staggered conformation, right? And when they are at an angle of 120 or 240, we say that they are the gauche conformation or the skew conformation, right? So the gauche conformation is a form that binds to the nicotinic receptor, while the anti-conformation or the staggered conformation, that's conformation that binds with the muscarine receptor, right? The difference in conformation results in different binding with the receptor. So here we have, this is anti-conformation. You can say that this is the acetyl group and this is the amine group. So both of these are 180 degree, right? So this conformation, that's binding with the muscarine receptor, while here we have these two at 260 degree. So because of the angle is 260 degree, then these two isomers, 240 degree, so these two isomers, they are in the gauche conformation, and here they are able to bind with the nicotinic receptor, right? The difference in arrangement, difference in conformation result in binding with two different receptors. So because the receptors are responsible for different biological activity, so these two groups, when they bind with different receptors, so both of these conformers will result in different biological activity. The next we have electronic effects. So electronic effects include the inductive effect, the resonance effect, the field effect, and certain polarizations that can occur inside the molecule. The electronic effects of various substituents, right? These effects have their influence on the drug's ionization and polarity. So drug will be ionized or not, to the extent drug will be ionized, to the extent drug will be polar or not. So all of these factors are dependent on the electronic effect of the substituent that are present on the drug, right? So these electronic effects, they determine how the drug can pass through the cell membrane or how strongly it will bind with the receptor. So what happens that now the drug is inside the system, it has been absorbed as passed through the cell membrane, now it is in front of the target. So it has bound with the target. So what type of interaction this drug will have with the receptor will be dependent on these electronic effects, right? So these are electronic effects which affect the biological action. Now we have the chelation effect. So some medicinal drugs can form chelates by forming a ring-like structure with the metal, and they bond within this medicinal drug. The metal is the coordinate covalent bond, right? So chelation affects the biological action, and how it affects the biological action, because whenever there is formation of chelate, the absorption of the chelate decreases, right? So some drugs form chelates with metals present inside the body. So there's different metals that are present inside the body, and if your drug binds with any of these metals and it forms a chelate, then such chelates show adverse effect. For example, we have hydralazine. This is hypertensive drug, and when this drug that binds with iron, which is present inside the body, then we have anemia. So instead of acting as hypertensive drug, it causes anemia, right? So chelates, when formed within the body, and if the metals are part of biological system, then we have some adverse effects. these chelates can have some beneficial effect as well. For example, if there are some heavy metals that are present inside the body, then these heavy metals causes toxic effect in the biological system. So since chelates form stable complexes with heavy metal and they are poorly absorbed, so therefore these can be used for the elimination of heavy metals by excretion, right? So what we do is that we have heavy metal toxicity, we use some medicines that are capable of forming the chelates, and these chelates are poorly absorbed and they can be easily excreted out, right? So in this way we can remove the heavy metals from the biological system. Then we have bioisosterism. So it's a very important strategy in the medicinal chemistry when you're studying about the structure-activity relationship. The bioisosters are the groups that have similar physical, chemical, and biological properties. So if you have to define the bioisosters, so these are the groups that possess near equal shape, volume, distribution of electrons, and have same physical-chemical properties and almost similar biological activity. Right, and why we use this modification, biosteric modification? The purpose is to synthesize compounds which are similar and they have retained the biological activity, but they improve selectivity and have reduced side effects. For example, if you have a structure, if you have a medicine, and the medicine has good biological activity, but the problem is that it has also some side effects. So what we do is that we make some biosteric modification. So it's important that bioisosteres, when they are used, they must have similar properties, whether they are physical, chemical, or biochemical. So these bioisosteres, they are used to synthesize the compounds that are similar in respect to the biological activity, but they have the advantage of improved sensitivity, selectivity, and reduced side effects. And they are produced by replacement of the molecular fragments, and these molecular fragments may be atom or functional groups. But the important thing is that these atoms or functional groups must have same steric electronic profile, means they should resemble in their sizes and the distribution of electrons and in their physical and chemical properties. So the bioisosteres must be same in the following aspects. They must have similar molecular size, they must have same electronic distribution, the degree or the type of hybridization must be same in all the bioisosteres, and the bond angle should be same, the polarity should be same, the lipid aqueous solubility, which we mean by that is which is also known as the partition coefficient, it should be same. The bioisosteres must have same chemical reactivity, the conformational factors, hydrogen bonding, etc., and the factors which affect bond formation ability, they should be same in all of the bioisosteres. So here are some classical bioisosteres. So we have monovalent atoms. So you can see deuterium, hydrogen, they are monovalent and they are bioisosteres. Similarly, fluorine, hydrogen are bioisosteres. So these are bioisosteres. The chlorine, bromine, sulfur with attached hydrogen and hydrosulfur. So these are also bioisosteres. Now we have divalent atoms as bioisosteres, so carbon double bond carbon, carbon double bond nitrogen, carbon double bond oxygen, carbon double bond sulfur, so they are bioisosteres of each other. Similarly, the CH2NH, if disubstituted, then we have oxygen if disubstituted, and sulfur if disubstituted, they are also bioisosteres of each other. Right? Similarly, here we have ring equivalents, so benzene and pyridine are equivalent to each other as well. So these are classical bioisosteres. Now we have some non-classical bioisosteres as well. So here we have this carbonyl and carboxylic group. So these are bioisosteres of each other. Similarly, the sulfonyl group and the sulfonamide, they are bioisosteres of each other. So these are all bioisosteres. So it means that in case if we have a structure with carbonyl group and we want to improve its activity, we can substitute this carbonyl group with a carboxylate group. Similarly, in place of hydrogen, we can have a fluorine group. So by these replacement of bioisosteres, what we have, we retain the biological activity, but the added advantage is that the side effects are reduced. Just for example, here we have two groups. Here we have aminopyrine. So you can say that here we have nitrogen here, right? So what happens that this aminopyrine, although it's biologically active, but it has side effect that it causes cancer. So what we do is that we carry out the isosteric replacement. We just replace this nitrogen with a carbon, right? And by replacing this nitrogen with the carbon CH, so what we happen that we retain the biological activity, but the side effect of carcinogenic property is reduced. Here we have again another example. So here we have paraminobenzoic acid, and here we have sulfonylamide. So this carboxylic acid and the sulfonamide, they are biosisters of each other, right? So replacing this carboxylic group with its bioisister result in increase in antibacterial potential for the sulfonylamide, right? So this is bioisister replacement. That's all for today's lecture. I hope you have understood it well. Thank you.